morning students. So in today's class we will be discussing about the decoding circuit for the cyclic codes. So as in the previous class we discussed about the encoder circuit as well as the syndrome circuit for the cyclic codes. Now we have a decoder circuit, so where as we studied in the case of linear block codes, so here also we are going to perform or use the decoder circuit for determination of the corrected error pattern. Okay, that means if the received vector has error, so then how we are going to correct the error using this decoder circuit. So now as you can see in the block diagram, so here we have the received vector, that is the input. That means the process of operation in the case of decoding circuit takes place step by step. So where in the first step what we are going to do is that we are going to consider the received vector. That means the received vector is inputted or is given as an input both to your buffer register as well as to your syndrome register. To buffer register and syndrome register. Okay. So that means whatever the received vector you are going to have, so that received vector it will be stored in the buffer register as well as it is given as an input to your syndrome register. So now the next step is you are going to find the syndrome bits. Find the syndrome bits and then store it in the syndrome register. Okay. So that means once you find the syndrome bits, you are going to place them in the syndrome register. So how we are going to find the syndrome bits? So you are going to find the syndrome bits by using the formula S is equal to R into H transpose. Okay. So where you are going to find the syndrome bits. So from this you are going to detect whether your received vector has error or not. So once the syndrome bits are found and is placed in the syndrome register, next step is in the third step. So we have the error pattern detector. That means we have an error detector circuit. So where error detector circuit is a combinational circuit. Okay, it is a combinational logic circuit where the purpose of this logic circuit is it is going to output 1. Okay. So it is going to output 1. So depending upon the syndrome register bit. So if the output is 1, so then we can say that it has error. That means your syndrome bit has error. The syndrome bit is having error. Okay. If your output is 0, then it does not have any error. Okay. So that means, so you are going to detect bit by bit. So you are not going to consider the whole received vector, but here we are going to consider in the syndrome register whatever the syndrome bits you have, you are going to detect it by bit. So the output of this pattern detector, depending upon the output of this, if the output is 1, so then we say that we have error. If the output is 0, so then the received vector is correct. So depending upon that, so you are going to output the corrected code vector here. So that means So buffer, in the buffer register also you have your received vector. So received vector is nothing but your z of x. Then you are going to XOR with what? You are going to XOR with your error pattern. So where you can see, so we have two inputs with respect to your corrected code vector, that is v of x. So one is your, so this is your e of x and this is your z of x. So which produces your v of x. Okay. So now, so this process of detecting whether your syndrome register has 1 or 0. So depending upon that, you are going to check that your received vector has error. So now if suppose if it has error, then what is the step you need to follow? So in the fourth one, if suppose if your output is 1, that means if the detector output is 1, so then it is fed back. Once again, we have some feedback connections there. So it is feedback. If output is 1, it is feedback to the syndrome register. To syndrome register. So until the error is corrected, and output is 0. Okay. So like this, it is going to check bit by bit, and then so depending upon if the output is 1, it is once again we have feedback connections here, it is feedback to your syndrome register, and then from the syndrome register it is once again given to your error pattern detector to correct the error, and then if the output is 0, so then we say that the received vector which was in error is being corrected. So this is the process what we are going to do for your decoding operation. So this process, that is this fourth process what we have, that is correction process, it is going to continue until it is checked with respect to each of your received vector. Okay. So how you are going to find the corrected code vector here? So where v of x is your corrected code vector, so you are going to get the corrected code vector with respect to your error pattern e of x plus your z of x. Okay. So how we are going to get whether your received vector has error? We are going to detect it from your syndrome register, that is your s of x. Okay. So that is how the process of your decoding operation takes place. So that is done with respect to this particular block diagram. Okay. So here we have a problem where G of D is given. You need to determine what is your G and H, that is generator matrix and the parity check matrix, and also you have to design the encoder circuit. So G of D is 1 plus D plus D plus 3. So we have D into G of D. So this is D plus D square plus D to the power of 4, D square into G of D, D square plus D3 plus D to the power of 5, D3 into G of D, D3 plus D to the power of 6. Okay. So now, so G is equal to, so it is 1, so rest will be 0, 0, 0. So this is for 7, 4. So next if we consider this one, so 1 is 0, so 1, 1, D3, D4, D5, D6. Then if we consider this, it is 0, 0, x square, x3, x4, x5, x6. If we consider this, it is 0, 0, 0, D3, D4, D5 and D6. So now, so this is not in the proper form. So this should be 1 0 0. So this should be 1 0 0, it is there. So it is 0 1 0 0, it is there. So we need to perform the row operations on these two columns. Now if we perform the row addition operation, that is row manipulation, so you have to replace the third and the fourth row. So this is done with respect to this one. So where you will be getting the generator matrix like this. Okay. So this is your generator matrix. Now we need to generate the H matrix. So H is equal to I of n minus k into P transpose. So n minus k means 7 minus 4 is 3. P transpose is transpose of your parity matrix. So this portion, so this is your parity matrix. So I have done the P transpose of that. So that gives your H matrix. Now we need to design the encoder circuit. So n minus k means we need to consider 7 minus 4, that is 3, that is G1, G2 and G3. So this is your gate and this is your enable signal and this is feedback from the input. So where we have 2 points here. So one is with respect to, this is your message input and this is your, that is switch 1 and this is your switch 2. So where it will be connected to R1 and this is your G1. So since we have G1 is equal to 1, G1 is nothing but your G0. So then output of this is given to an XOR. So we have the encoder circuit which I have written it here. So where we have considered G0, G1 and G2. So since it is 3, so we need to consider G0, G1 and G2. So where we have G0, so with respect to your generator polynomial given, we have G0, G1 and G3. Okay. So your G2 is 0. So but we need to consider only 3 G's here, generator polynomials G0, G1 and G2. So here G2 is equal to 0. Okay. So with respect to G0 we have R0 and then we have G1, R1, G2 is 0. So it is directly connected to your R2 and then it is given to a modulo adder. Okay. From the modulo adder, so it will be given to your AND gate input. So depending upon the enabling of your switches. So first initially switch 1 will be connected and later on switch 2 will be connected to output the data. Okay. So this is the solution for this problem. So we have a problem here, that is the generator polynomial is given. So we need to find the code vector in systematic form for the message d of x equals x square plus x to the power of 3 plus x to the power of 4. So how you are going to find the code vector with respect to the systematic form? So we have the formula, that is x to the power of n minus k into d of x divided by your g of x. So this is how we are going to find the code vector in the case of your systematic form. So what is your x power n minus k here? So it is x to the power of 15 minus 7. So 15 minus 7 means it is x to the power of 8 into your d of x. So what is your d of x is x square plus x to the power of 3 plus x to the power of 4. So which is equal to x to the power of 10, x to the power of 11 plus x to the power of 12 divided by your g of x is 1 plus x power 4, x power 6 plus x power 7 plus x to the power of 8. So it is x to the power of 8, 7, 6, 4 plus 1 divided by x 12, x 11, x 10. So it is x to the power of 4. So it will be x to the power of 12, 11, 10, 8 plus x to the power of 4. So we are left with x power 8 plus x to the power of 4 plus 1. So it will be x to the power of 8, sorry, it will be x to the power of 8, x power 7, 6, 4 plus 1. So we have x power 7, x power 6 plus 1. We have x power 7 plus x power 6 plus x power 1. So this is your r of x. So v of x is equal to r of x into your d of x. So what is your r of x? So we have how many number of bits should be there? So it should be 15 bits. So 15 bits means so your d of x is given as, so we have x to the power of 0, that is 1, it is 0, 1 is also 0, so it is 2 and 3 and 4. So that means we have 5 bits of your d of x. So 5 bits means rest of the 10 bits should be your r of x. So from the given r of x, so we have 1, x is 0, x2 is 0, x3 is also 0, x4, x5, x6 and x7. So that means 1, 2, 3, 4, 5, 6, 7, 8. So this is your r of x, okay. R of x coefficients. Then this is your message vector. So this is 8 bits. So that means rest of them should be your d of x. So this is your 1, x power 1, x square, x3, x4. So we also need to write x6, x5 and x6. So this is your 7. So this is your 8 bits of r of x, and this is your 7 bits of your d of x coefficients. Okay. So together the length of this message vector is how much? So the length of this is 15 bits. Okay. So 15 minus 7 means, so n minus k means how much? So n minus k will be 15 minus 7, so that will be your 8. So your r of x will be your 8 bits and the remaining will be your d of x. So this constitutes totally the 15 bits. So this is the vector v of x, what we have found out with respect to the systematic form. So now in the problem they have given that assume that the first and the last bit of the code vector for d of x suffer transmission errors. Find the syndrome of v of x. So that means if this is your message vector, that is your v, this is your code vector v of x. If the first bit as well as the last bit, so if they suffer error, so if they have error means what? So instead of 1, so if it is 0, 0, so we have 4 zeros, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So instead of 0 it should be 1. So now, so this is the error in first and last bit of your v of x. Okay. So that means this bit as well as your this bit. Okay. So now if we consider this, so what will be your expression? So this will be 1 x square 3 4 5 6, that means x power 6 plus x power 7 plus 8 9 10 11 12 13 14. Okay. So this is the expression what you are going to get. So now we need to find what you need to find the syndrome bits, that is S of x. So now in order to find your S of x, so S of x is found out by how? So it is Z of x, that is received vector, divided by G of x. So what is your received vector? So it is x power 14 12 11 10. So this has to be divided by your G of x. So we have G of x, that is x power 8, x power 7, x power 6 plus x power 4 plus 1. This is your G of x. Okay. This is your Z of x, which is we have considered from here. So it is x power 6. So it will be x power 14, 7, 13, 12, 10 plus x power 6. So 12, 10, 6. So it is x power 13, 11 plus 7. So next is x to the power of 5, 13, 12, 11, so 9 plus x to the power of 5. So we have x to the power of 12, 9, 7 plus 5, x power 4. So then this will be x to the power of 12, 11, 10, 8 plus x to the power of 4. So we have x to the power of 11, 9, so x power 10, 9, 8, 7, 5 and 4. This x to the power of 3, so it is x to the power of 11 plus 10, 9, 7 plus x to the power of 3. So we have x power 8, x power 5, x power 4 and x to the power of 3. This plus 1. So this will be x power 8 plus x power 7. Then we have x power 6, x power 4 plus 1. So then these two gets cancelled. Then we have x power 4 and x power 4. So we will be having x power 7, x power 6, 5, 3 plus 1. Okay. So this is your plus 1. So this is your S of x, that is your syndrome bits. Okay. So this is your syndrome bits and this should be your n minus k bits. That means 15 minus 7, that means you should have 8 bits as your syndrome bits. So where this is 1 plus x power 3 plus x power 5 plus x power 6 plus x power 7. So where you can write it as 1, 0, x square, x3, x4, x5, x6 and x7. So this is your S of x, which is of 8 bits. Okay, we have the next problem, that is a 15,5 linear cyclic code which is given by g of x, and we need to draw the block diagram of encoder as well as the syndrome circuit, and also we need to check whether v of x is a code polynomial, and also find the code polynomial for the message polynomial d of x in the systematic form. Okay. So where I have written g of x, that is the encoder circuit by considering g of x. So we have n comma k as 15,5, that is 15 minus 5 is 10. So we should have the g values from 0 to 9. So where depending upon whether g values is there, so we have provided the connection. So those many registers will be there. So we have G0, so G0, G1, so G0 and G1 is there, so G2, then G3 is not there, so G4, G5 and G8. So since we need to represent only up to 9, so we have considered 9 registers here. So this is the encoder circuit for the cyclic code. So similarly you need to write the syndrome calculation circuit. So in the case of syndrome calculation circuit, the only difference what we have is, instead of R0 you are going to replace that by S0. Okay. So where the received vector you are going to input it from the right side. So you will be having first the received vector, and then the connections will be similar like this only. So where you can write the syndrome calculation circuit. So here they have asked to find whether d of x is given, you need to represent them in the systematic form. So how you are going to find it in the systematic form? So where you know the formula, that is x power n minus k into d of x divided by your g of x. Okay, if you do this you will be getting your code polynomial, that is v of x. X power n minus k means 15 minus 5 means it is x power 10 into your d of x means it is 1 plus x square plus x to the power of 4 divided by g of x, that is 1 plus x square, x is 4, 5, 8 plus 10. So this will be x to the power of 10 plus 12 plus 14 divided by your g of x. So now divide g of x with respect to your numerator. So g of x is what? So g of x is x to the power of 10, 8, 5, 4, 14. So if you divide 14, 12, 9, 8, 6 plus x to the power of 4. So we have x power 10, 9, 8, 6 and 4. So plus 1, x power 10, 8, 5, 4. So we have 9, okay. So this is your R of x. So where R of x is what? So it is 1, x is 0, x square, x3, x4, x5, x6, x7, x8 and x9. So we have 10 bits. So what is your d of x? So d of x is 1, x is 0, x square, x3 and x4. So this is your 5 bits. So totally we have how many number of bits? So totally we have 15 bits. Okay. So this is the second sub question what we have done. So now we need to check whether v of x is a coord polynomial. So how we are going to check whether v of x is a coord polynomial? If the remainder polynomial is completely 0, so then we say that v of x is a coord polynomial. If we get a non-zero, then we say that it is not a coord polynomial. Okay. X power 10, 8, 5, x square, x plus 1, x power 14, 8, 6, x power 4, 18, 12, 9, 8, 6, 5 plus x to the power of 4. So we have 8, 6 and 4. So it is x power 12, x power 9, x power 5 plus 1. So it is x square, x 12, 10, 7, 6, 4, 3 plus x square. So it is x power 10, 9, 7, 6, 5, 4, 3, 2 plus 1. So it is plus 1. So we have x power 10, x power 8, 5, 4, 2, x plus 1. So x 10. So 5, then 4, x square, 1 and 1. So we have x power 9, x power 8, x power 7, x power 6, x power 3 plus x. So that means the remainder is not, so your r of x is non-zero. So that means it is not a coord polynomial. It is not a coord polynomial. Okay. If r of x is 0, that means it is a coord polynomial. Okay, this is how we are going to check whether it is a coord polynomial or not. So this completes the fourth module. Thank you.